on Monday, and it used to work. But today, for some reason, it's not working. So I will check the settings. I will check the settings, and well, if it doesn't work, we go on. But I'm sorry for that.
Okay, not a problem.
Hello. So today we're going to look at a real case study.
It doesn't seem to work for some reason.
That is the reinterpretation of old well-tested data
Yes.
and results.
How many participants are we? 32?
For a tight gas sandstone formation
12. Yes,
in the context of an exploration project.
Join
so
just a minute.
Three keywords here, and that should be mentioned again. Reinterpretation, that is a common practice when it comes to well testing, analysis, and especially dealing with really old data that can add some value to any type of project, whether it's exploration, appraisal, or field development. In this case, it was used in real life for an exploration project. As you may know, most major oil companies have really well-defined processes for exploration project when it comes to geophysical evaluation and data acquisition, geological interpretation, and petrophysical data acquisition and interpretation. The problem is quite often they tend to underuse and underestimate the value of old well testing data and results. And that is frankly a loss, because conventional G&G evaluation can give you an idea about the location of the formation, its thickness, its hydrocarbon content, and even some of the properties, some extrapolated properties when it comes to permeability and porosity. But of course, these are sometimes not as accurate as well testing results. This can be a challenge, because when you think that companies put a lot of money, can be $60 to $80 million on a survey, on a data acquisition survey for 2D or 3D information, and then this data is extremely costly, and on the other hand, they don't use available data regarding well testing. And when you think that these data are the only one that can give you some real idea
good evening, everyone, and welcome to the University of Basra SPE student chapter. Let me introduce myself. My name is Abdullah Raad, the president of the University of Basra chapter. As you know, today our webinar titled "We'll Clean Up in Tight Gas Wells," presented by Mr. Ali Sharif. Sure, we are blessed for him to be with us for the second time and present our webinar in our chapter. Let me give you a brief introduction about our presenter today. Mr. Ali Sharif is a senior reservoir and production engineer with more than 10 years experience. Worked on a range of fields offshore in the North Sea and the Norwegian Continental Shelf, also on the onshore in the north of Africa. Graduated from the University of Sorbonne in France. Now, Mr. Sharif, you can start, please.
They should implement
Thank you, Abdullah.
Use in future exploration projects.
Well, maybe some of you have attended the previous course, which was entitled Well Testing in Tight Gas Formations. So those of you who have attended the previous lecture will have some more elements. I haven't put as much background in this one, but I will try to compensate by speaking. This lecture is not as long Last time it was 1 hour. This time it will be about 35 minutes. But so I will have time to speak slowly and take as many questions as needed. So yeah, the title of this course is Well Cleanup for Old Well Test Results in Tight Gas Sandstone, and that's in the context of an exploration project. We can move to the next slide. Yes, thank you. And look at different things. We will look mostly at the gas PI within this gas column interval. And for these tests in the gas column had bad cleaning. So the game here is to try to discriminate between tests that are valid and the tests that are not valid, based on how good was the cleaning of the well. So the method used here is probabilistic. It's not an absolute, but because we had a lot of information, you have in this big scale, and on the x-axis you have the reservoir drawdown. And I consider that a good idea, because it's tight formation, to know whether we have mud cake formation, which is the consequence of bad cleanup or not, is to look at the drawdown level. So if in these blue points you have a lot of old DST from the 50s and early 60s, and some points that are more modern tests from the 80s with the modern cleanup. And you can see two different ensembles. The one on the left is for a small drawdown around 30 bar. And for those ones are interesting because it's a tight formation, we know that very likely or very certainly these points they do not categorize for bad cleanup, and that most of this drawdown is due to the tight gas formation. So we don't have bad cleanup situation. So we can possibly exploit this old DST within this ensemble. Now, if we go to the ensemble on the right, they have very large drawdown, and it is likely, not certain, but likely, very likely, that part of this is due to tight formation, but another part of this drawdown is due to the bad cleanup. So, in this circumstance, as I wrote, the tight formation is not the only responsible for the flow restriction, and mud cake that has clogged significantly the borehole is likely to occur. So now, this being said, this statement is valid for the old DST within these points. Some of the modern DST that can be on the ensemble on the right, they may still have a proper cleanup, and so they will still be exploitable. And in this case, the drawdown is due to the tight gas formation only. We can move to the next slide. Thank you. So yes, let's go through it quickly. As I said, the choice of most valid point to be exploited for production index is multifactorial. So you have the link with the cleanup, and as I said, the method used is not absolute, but it doesn't create a causality, but it creates a high likeliness. It's just a way to evaluate the likeliness of good cleanup. One other factor that we will use in the rest of the presentation is to check whether radial flow stabilization has been reached, or if we are reasonably close to it for the bottom hole flowing pressure. Now, just as qualitative element, we can look at the gas flow rate. We can, if it's high or not, we can look at the production index. And any information or comments or observation noted for each well intervals can be useful. Sometimes you can find that you only have traces of gas during the DST. Sometimes you find no significant gas production, but you find traces of gas in the mud, for example. So we will evaluate from the points you've seen before, the blue points. We will now only select those who have reached a radial flow stabilization or close to it. So let's move on to the next slide. The third slide, yes. So as you can see, we still have this logarithmic scale. We still have the same scale for the reservoir drawdown, but we have much fewer points. In the old DST with small drawdown, you have delta 1 well, and we only kept this one because we have only 2 points on the left, one pink point and one very small blue point or indigo point. So for the old DST, the ones that have reached stabilization, these are only these two. So one for delta 1 well and one for a well called sigma 1. So which has not reached radial flow stabilization but is close. So delta 1 and sigma 1. And if we go to the right, we have a few other wells that we have kept because they were modern, not just modern wells. There is old wells, modern wells, but they have reached radial flow stabilization. So you have both. And I want to mention one that is called Alpha 1. The point is very hard to see, but it's about at 84 bar drawdown, and it's close to 10 in PI. And this Alpha 1 well is a modern DST. That's why we kept it, because it has good cleanup. So what we know for this well is that we will have a good evaluation for the production index, because we have also reached radial flow stabilization. But it's potentially bad evaluation for the production index if the well was badly cleaned up. And as a matter of fact, even if it was not, even if it was a modern DST, we have the information that it was not properly cleaned. So that's why I'm saying we have to be careful for the production index. And additionally, although it was not cleaned in the with the perfect standard, it should be noted that it was not left to rest with the bentonite in the bottom of the well like the old DST in the 50s or 60s. So we can go to the slide 4, and I suppose we have a summary of the wells that I mentioned. So the one of them was, as you see, the first one has drawdown 20 bar. It was drilled in 1962. It has stabilized pressure, reliable cleaning, so it can be exploited. The second one is Sigma 1. It's not stabilized radial flow, but is very close to it and reliable cleaning. You can see it's also at small drawdown, so which is a second confirmation that we have no mud clogging. And the Alpha 1 well, which is more complex, has a large drawdown, but we believe that that even if it's not cleaned up, it didn't rest. The well didn't rest with the mud at the bottom too long, and it has stabilized the radial flow. So probably for this one, we cannot exploit properly the production index, but we can. That is 195 cubic meter per day per bar, but we can probably trust the reservoir pressure that is measured. We can go to the next slide now. Okay, so now we are moving from the gas column to the oil column, and we will look at two things because these oil column intervals, they are producing gas and oil, and when it's yes, they're producing both. So we first look in this slide at the gas production index. These are reported for both modern well tests and old well tests. So as you check the column on the left, you have some modern well tests like beta 1, beta 2, and some old DST conditions, beta 3, and on some interval and gamma 1. You can see that they lie at small drawdown. So we are confident that the cleaning was proper, as was written. We have gas PI that is reasonably high. And so we believe there is no significant mud cake impact on the drawdown. As well, we have gamma 1 that has not been well cleaned at first, but it was acidized. So we believe that this acid job did the job in terms of cleaning the well. And we can reasonably trust the gas PI that comes from it. I should note though that when you, in theory, the PI is not dependent on the choke. There is a calculation to get the PI non-dependent on the choke. But as you measure this PI, they have a dependency to the choke size. Yeah. But I will not elaborate on this in this lecture too much. We can go to the next slide. Yes. So now it's still testing column, but for the oil production index. So in most of the old DST type, the well has not been properly cleaned. With some exception, like beta 3, we saw in the previous test that it was cleaned up reasonably well, and we have a small drawdown, so we can trust the production index that comes from it, about 9 meter cube per day per bar. And if we move to modern tests that happened in 58, 64, or happened in the 80s, but were practiced with more modern standards, they have good proper cleaning before production. So we can trust beta 1 for the oil PI, 1 to 3 cubic meter per day per bar, and beta 3, which has about 1 cubic meter per day per bar. And now there are some correspondence between well where we know they were properly cleaned for gas, or we know they were properly cleaned for oil, like for beta 3. And we have the well I mentioned before, that is gamma 1, that has not been properly cleaned at the beginning, but was acidized afterwards. And so this PI can be trusted. So overall, as I said, when oil was the dominant phase, most of the wells, I'm not saying in general, but for this field, most of the wells benefited from good cleaning conditions before testing and show a range of PI from 1 to 9 cubic meter per day per bar. So the idea, this is not general, of course, this is the best you can get from information provided for one field. So I just give you an angle of approach where you have a field with some difficult data, how to make sense of it and know which test to trust and which test not to trust. So we can finish with this presentation and move to the video. We have a video on a supercharge.
Yes. Just a second.
Yes. Abdullah, I will make just a comment about this video before we start.
Okay.
Should I start now?
No, just
sure, no
problem. I will share it.
Mm-hmm.
So supercharge is quite...
Yes, Mr. Sharif, you can take your comments.
Okay.
Quite relevant.
We'll just make a comment before it starts then. Yes. I have spoken last lecture about tight gas formation, now about cleanup in tight gas. I just wanted to mention supercharge as a bonus course because supercharge is a very common occurrence in tight gas formations. Typically here we will look at overbalance drilling in a tight gas formation. If you look at this plot, you will see that in the drilling phase, you have this increase of pressure at the bottom hole gauge because of the mud weight. And then when we put the casing, the pressure is locked between the casing and the near wellbore area because it is locked, so it's constant. You have this constant phase. And when we and then there is an accumulation of pressure near the. When we drill, you have an accumulation of pressure near the wellbore area because it doesn't have the time to dissipate in the formation. That's why you have this pressure during casing phase that is higher than reservoir pressure. So the casing locks the pressure, so it seems constant for a while, and then the pressure slowly dissipates. So if you waited for a good time for the pressure to dissipate and that you started doing the production test, then you get the normal reservoir pressure that is on the green line. But you can imagine that if you don't wait for this, and this can take quite a while, and you take the production test during the red area, the red zone, then the testing will give you an overestimate of the reservoir pressure. You can easily understand that. So now we can start the video and you will have more explanations.
A few factors come into play in such a case: the tightness of the formation and eventually the mudcake. There are numerous studies about mudcake influence, as well as tight gas formation influence on supercharge, and even conventional formations. If someone challenges you with the effect of potential supercharge on the PI of quite relevant, supercharge is quite relevant for tight gas formations. A few factors come into play in such a case: the tightness of the formation and eventually the mudcake. There are numerous studies about mudcake influence, as well as tight gas formation influence on supercharge, and even conventional formations. If someone challenges you with the effect of potential supercharge on the PI of the predicted PI of a formation in a conventional formation, so supercharge is quite.
Sorry, the sound doesn't come out.
Okay. We can stop it. It's okay. We can just leave the plot. It's not dramatic because I actually explained most of it in my introduction.
Okay.
The only thing I want to say is, I want to make another comment on supercharge. You see, supercharge, of course, can happen even in conventional wells. But sometimes you can find a manager who puts too much pressure on junior engineers, reservoir engineers or production engineers. And when you build the model, they tell you, have you checked the supercharge? And I think that's too much pressure put on a junior reservoir engineer, because when you build a model, you don't have much time to fix everything, every detail. I mean, you build a model, then you improve it. But and it's usually something I would overlook if I was working on a conventional well. If I have, for example, 300, 400 millidarcy well, I would not look at supercharge when I build the model. I would build the model, run it, and maybe look at it 6 months later to improve the model. Because I deem it very unlikely that supercharge happened with such a good permeability. But of course, when you deal with tight gas formation, then you should look at it systematically. Yeah. I have finished as far as I'm concerned the presentation. I'm ready to take questions. Yes.
Thank you, Mr. Sharif. Anyone have a question?
Yes, I have a question. So may I ask you, Mr. Sharif? Good evening, all.
What did you say? I don't hear you.
So may I ask you, Mr. Sharif?
Yes.
So, okay, so I have 3 questions. I would start with the first 2 questions. As per my knowledge, when we are talking about the well, the first thing that we'll define, or the first thing that we'll take in our consideration, is the well type, whether it was vertical or horizontal. So in your presentation, you did not, talk about this point. So could you please just explain whether is that necessary? I mean, is like going to consider or not? So this is the first question.
Yes. Okay. Go on with the second question.
Yes. The second question that I have. So in the first slide that all of it was good cleaning. The third point, which is beta 3 or the cleaning, there was not mentioned the choke size. So just a curious question. I mean, there is there is production, but there's no choke size. What is the reason? And the last question that I would have, which is about the supercharge in conventional well. So let's say if we have like a conventional well here in south of Iraq. I mean, the only solution for this point or this problem is just run the casing, or is there any solutions or methods we can deal with? So that's all I have. Thank you.
Okay, thank you. The sound quality was jumping on and off, so I will start with the beginning. I forgot to mention the geometry of the well, and even some of its completion. And the reason for that, I actually forgot about it. But as you mentioned it, it's extremely important when you do a DST. The reason I forgot it is because these are very old DST from before the independence of the country, and some from the early 80s, and they did all the well vertically. They drilled all the well vertically, and most of the time with open hole conditions. Yes, so that's the answer to the first question. The next question, I'm not sure I got everything right, but you said that the choke size was missing in some of the slides. And the thing is, especially what we are dealing with is old information, that some of the data are missing. That's just as simple as that. Some of the data were simply not written. And the last question is about conventional wells and supercharge. There is nothing to do with completion. The casing, whether you put a casing or not, whether you have a perforated casing or open hole condition, and that you lock the production at a higher level, that's up to you. And there is nothing about mitigating the supercharge problem using different casings. The only thing I recommend is that you wait long enough, if you can, for the supercharge to go, so that when you test your wells, you have a good DST, or that actually you still do the DST when you're in supercharge, but there are many analytical ways to evaluate what part is supercharged and what part is not. I would recommend you the videos by, I will write his name, the videos by Louis Matar on this subject. He has made a software that is now AHS software, and they have some modules within the software for tight gas. This is, as far as I know, some of the best work that has been done software-wise on the subject. I wrote his name wrong. I will write it again. Louis Matar, like this. Yes.
Okay. Thank you so much, Mr. Sharif. Thank you for answering all my questions. I appreciate it.
My pleasure.
Yes, anyone have another question? We have 5 minutes for taking your questions. If there are anyone who would ask, Mr. Ali.
If there are no further questions, maybe eventually we can wrap it up. I don't know.
Okay. Dr. Amani, can you?
I just want to say thank you to the University of Basra SP chapter. Thank you, Abdullah Al-Shams, Dr. Al-Shams.
Thank you. Thank you.
And thanks, Dr. Amani Al-Husseini as well. Yeah, it was a real pleasure.
We are all thank you, Mr. Ali, to have this webinar.
Great.
And we wish to have another webinar in the future.
Hopefully. And I salute all the people who came. I hope you got something from it. Yeah.
Yes.
Yes.
Okay. Thank you.
Thank you. Bye-bye. Take care.
Bye-bye.
Thank you.